I'm going to go more into the history, try to give you an idea of the history of this subject. So this is maybe a historical perspective of dynamics. So in 1666, we've got Newton basically inventing calculus. And also explains planetary motion. So I guess you could say he invented ODEs, ordinary differential equations, which will be one of the main topics we look at. And so things that he didn't like the three-body problem, he just decided, I can't solve it in closed form, so I give up. But nowadays we wouldn't give up. Poincaré didn't give up. So in the 1700s and 1800s, so we're speeding through a lot here. There was a lot of development of classical mechanics and mathematical machinery to tackle those problems. And then, in the 1890s, we've got Poincaré. And what does he do? He initiates the geometric approach to understanding dynamics. Maybe we'll call it nightmares. I don't know if he really had nightmares. I think maybe nightmares of chaos. And he wouldn't have applied the name chaos. I think he used this idea of something called a trellis or a tangle. And by trellis or tangle, we're talking about a tangle of trajectories. Unfortunately, Poincaré wasn't very good at drawing. So even though he thought in pictures and geometry, he didn't provide many drawings. But this is kind of one of his nightmares, and they're not terrible. What is this? Over there, there's a point here. Where's my pointer? Ooh, okay, cool. Yeah, so this point here, this dot is like a fixed point, meaning under the dynamics, things at that point do not move. But then these arrows give the idea that there are two directions. There's one direction where if you start along that direction, you will move away, either positive or negative, and the other direction where if you start along that, you will shrink towards this fixed point. And he had this picture in mind of there are directions that are leaving and approaching a fixed point, and they can intersect in ways that are nightmarish. I don't know about all that. This is sort of a movie showing how things move through this. This was calculated for a pendulum that is shaken. And so you've got the fixed point. I guess you can't see it. The fixed point, I need a different color for this. How about purple? Okay. So over here, there's a fixed point, and emanating out of it, there's the blue direction is leaving and the red direction is approaching, and we're seeing kind of blobs of initial conditions in the space moving around. So I'm giving you a 30,000 foot view. I don't expect you to understand exactly what's going on here. Just this is sort of an engine of chaos, and Poincaré saw it. And to give another illustration, this was actually a calculation I did. This is related to my work on understanding environmental flows. So what we've got here, maybe you can see the coastline of Florida. This is Florida. So this is a view of the atmosphere. We got Florida, and then Virginia's somewhere up here. This is a hurricane. The first hurricane of the 2007 season. So it was named, and the first hurricane starts with A. So this was Andrea. And this has the same kind of structure that Poincaré had nightmares about. So we could define, there's something like a fixed point here in this flow. And if we follow these things that are blue and red, these are sort of directions in which fluid particles are moving towards the fixed point. But it defines the inside of this hurricane, so the hurricane vortex. And we could also define regions that, based on the geometry of that tangle that Poincaré imagined, some of these things will get inside the green blob here. Actually, this green kind of twisted rectangle will get entrained into the vortex. This little magenta thing will go out, and this purple thing right next to the green will actually stay out if we follow this forward in time. So if you follow it, you can see that the green indeed goes in, and both kind of purple and magenta things stay out. So if I go back to, we kind of froze time when there was another, let me freeze it. So that's what the vortex looks like at a later time. And so that's kind of interesting. And this is all just based on topology, and we'll talk about it at a later point. I kind of like this screen, but I was going to share again. Or do I really want to? Well, let me show this. Okay, this is a marble. It's actually kind of like a small solar system, but this is a marble in a weird surface with, it's a machined surface with 4 bowls connected by saddle points and a hilltop in the middle. And when this marble is released, it's hard to predict what, it's released from rest, rolling without slipping. It's hard to predict where it will end up. So let me just let this play. So it ended up there. But you see, it kind of, it reaches these points where with the slighter, bigger nudge, it could end up in a totally different well. And this kind of visually shows the idea of chaos, at least in a mechanical system. If we were to slightly change the initial condition, if we release this somewhere slightly different, it could end up somewhere totally different. So we release it. Like, oh, where's it going to go? Oh, okay, it stays in that well. But it was pretty close to almost getting into this one, right? And maybe if we released it from slightly different point, it would end up in this well down here. Who knows? So Poincaré, even though he didn't call it chaos, he could sort of see with his geometric method this idea of sensitive dependence on initial conditions. So that's kind of the main point. Getting back to this. So chaos, what you should think of chaos right now is, I mean, it is more than this, but is sensitive dependence of behavior on initial conditions. Just think of that in the most qualitative way, okay? All right, so the end, unfortunately, because Poincaré did not draw much, a lot of his stuff was left in obscurity. So not much happened with him and his work. So that's kind of a bummer. There was some work though in the around 1920 to 1950. There was work on, hopefully you know about the harmonic oscillator, which is a linear oscillator. There was a lot of work during this time on nonlinear oscillators in both physics and engineering. There's people with names like Duffing, who studied the Duffing oscillator. There was also an appreciation during this time of complex behavior in Hamiltonian mechanics. And this is due to mainly four, I think they're mostly known as mathematicians. There's Birkhoff, Kolmogorov, who also has his name is attached to turbulence. Arnold, right, Arnold, and Moser. Interesting note, I got to see Arnold. He was very old, but when I was like a freshman, this mathematician I worked with at JPL said, "Oh, Arnold's going to give a talk. You have to see him." I'm like, "Who's Arnold?" But I'm glad I heard his talk. I think he's passed away, and I don't know about anyone else on this list that I've actually seen in real life. So there was appreciation about complex behavior, kind of like that marble moving on the surface. But they proved things. So there was something proved, in particular K, A, and M. Kolmogorov, Arnold, and Moser had something called the KAM theorem. I'm sure they called it something else and did it individually. And I guess there was no Google, so they couldn't Google each other. But they came up with the same result within a few years, so now it takes their names. KAM theorem. This is related to chaos in Hamiltonian systems. The proof itself isn't terribly useful, but we know that there is chaos in Hamiltonian systems. And what do we mean by chaos? Here, chaos, I set up here sensitive dependence of behavior on initial conditions, but what's needed, and this is what was kind of interesting and surprising, we're talking about a deterministic system, meaning what comes later follows exactly from what came before. There's no randomness, no stochasticity, and yet there is this element of lack of predictability. After some time. So think of the weather, especially, here in the New River Valley, it's notoriously difficult to forecast the weather. Like, I don't trust the weather forecast 48 hours ahead of time. In Southern California, I did. Oh, it's going to be sunny and 70s. But here, I don't trust it, because even though this is governed by the laws of physics, it is a chaotic, deterministic system. So, which is good for us, I think. Neutron stars don't have much of an atmosphere, but it's very stable. And I'm glad we don't live on a neutron star. All right, so this was like 1960. I said 1950, let's say 1960. And then the invention of the computer, right? 1960s, computers become available for researchers, often driven by the Cold War. And in the early 1960s, professor at MIT named Lorenz, he comes up with a simplified deterministic model with three states. So he comes up with a 3-state ordinary differential equation for the atmosphere. It's a pretty terrible model of the atmosphere, but it has some interesting properties. So he found what's called as a strange attractor in his simple model of convection. And at first he thought his computations were doing an error, because at this point we're talking 2 or 3 generations after Poincaré. It's kind of been forgotten that there could be this instability kind of generally found in dynamical systems, but Lorenz sees it. So I'm gonna go back to my other camera. Oh, look, there's that marble again. So maybe you've seen this butterfly diagram. So this is this famous picture of the Lorenz attractor, and so the initial conditions down there, and then it just sort of, it either wraps around the left thing or the right thing. Let me show you a video that kind of shows this system. So this is the Lorenz system. It's 3 ODEs, so dx dt, dy dt, dz dt. There isn't even much nonlinearity. There's an x times z and an x times y, but the way that the state moves around is rather unpredictable. Like you can't, it'd be hard to, just looking at it now, okay, is it going to keep going around that left lobe, or oh no, it's going to turn around and go to the right? No, it's. So if we looked at x as a function of time, and maybe that's later in this video. There we go. Okay, so now we're sort of plotting x as a function of time along that x-axis. And this is important when you relate to measurements. Sometimes when you're just taking a measurement of something, you'll only get a time series. So you'll get something like this red time series that's being drawn on the bottom here. And could you, from that, infer what the actual system is? But now we can just sort of look at time series and you can kind of see, oh yeah, that's chaotic. But this was the Lorenz system was pretty interesting, at least for Lorenz, because he got this sort of lack of predictability, not because it wasn't deterministic, but because it's a system that exhibits chaos. So this is just showing that down here, the bottom, this point O, there's 2 initial conditions, one's red, one's blue, and they follow each other around for a while. And then at some point, I guess it comes back down here, it separates, and then they go their separate ways. No, it's coming down here. Come down here, and then the red trajectory goes that way. So if this is the beta variable here, that's why we're showing beta as a function of time. I think it's the same thing as x from before. One goes to negative, and the other one goes to positive. So that was at this point here. So the 2 seem to be matching up, but because of just a very slight difference in initial conditions, you start to see it's dramatically different behavior. It's dramatically different when one of these shoots up to positive values and the other one shoots down to negative values, okay? So they seem to match each other and then they lose all coherence. And that's sort of the essence of a deterministic chaotic system. This is not due to noise or anything like that. It's inherent in the actual solutions of the differential equation. Okay. So that's some cool stuff. Okay. Then what came? Well, unfortunately, I said Poincaré, nobody listened to Poincaré. And you can actually read this paper, maybe I'll post it. It's a pretty good paper, but it was in a journal of atmospheric science. And so it didn't get many views. These days, you would need to publish something in one of the top journals like Nature or Science or Proceedings of the National Academy of Sciences to get attention by a large group of people. So other atmospheric scientists saw this model of Lorenz and they just criticized it. Oh, this is a terrible model of the atmosphere. They didn't appreciate the larger implications. I think Lorenz did, which is good, and so stayed with it and became sort of a pioneer of the sort of computer age of chaos. And now computers run our lives. No, I'm just kidding. No, computers are a good thing. I like computers. But yeah, so Lorenz stuff kind of didn't have much visibility. Didn't get picked up by the larger scientific community. It's a good thing he published it though. And this is back in the days when you've probably heard people say, oh, back in my day, computers had punch cards. Well, that wasn't back in my day. I kind of grew up with MATLAB, so I've used MATLAB since I was a freshman in college. I don't know anything about the punch card thing. So then what? Kind of the decade which was the main flowering of appreciation of nonlinear dynamics and chaos was the 1970s. And there was work by Ruel and Takens. They kind of picked up on this thing from Lorenz and said, huh, he looked at just a 3-variable system of what is actually the fluid continuum. Maybe the Navier-Stokes equations, maybe Navier-Stokes, if you don't know, Navier-Stokes are the main fluid equations of motion. It's a partial differential equations. And so they speculated, I don't think they proved, that it has chaotic solutions. And maybe that's what gives rise to turbulence. And so turbulence is considered one of the last great unsolved problems of physics. Like, what is turbulence? Is it actually related to chaos? We don't know. We don't know. So they just speculated. That was 50 years ago. So if you take as your project, I will solve the problem of turbulence. You'll probably get a Nobel Prize or something. What came next? Somebody named May, I forget their first name, looked at an iterated map. So iterated maps are simpler than ODEs. An iterated map would be something of the form, if you have a state X, then, so you basically discretize time, if you want, and so xk, function of xk gives rise to xk plus 1, the next thing. So this is called a map, or iterated map, or discrete map, and it is the most fundamental dynamical system. Ordinary differential equations can be put into map form. In fact, that's what the solvers do when you just sort of say solve ODE. It's creating a map that takes in the state at an initial time and spits out what's the state at some final time. So maps are the most fundamental. What May did was look at a one-dimensional map related to biology and population dynamics. So it was a population dynamics model. Called the logistic map. And it's just a 1D map. So, right, k is just a real variable. And he showed that there's a certain value of the parameter. Let me write it this way, f x k, and then I'll put parentheses r. There's some parameter r. And for some values of the parameter r, ranges of the parameter r, you actually get chaos. So that was a major contribution. This was also published in nature. So it got seen by a lot of people. Let's see, maybe I could just sort of show it. Not this. There we go. That's the logistic map. Very simple. They use N instead of K, but same thing. What I'm showing, what's being shown here, this is a bifurcation diagram. So on the horizontal axis, that's the parameter R. On the vertical axis is the location of stable points, stable population points. So you see this sort of characteristic, it goes straight and then it branches and then it branches again and it branches again. And you've got this weird chaotic looking web thing. So this is now an iconic picture of chaos. So this sort of says, shows the importance of what are called bifurcations. Bifurcations are qualitative changes in the behavior of a system as you vary parameters. So that's also going to be something we talk quite a bit about. There were some experimental studies of chaos, so by many people, some of whom I know. And then related to chaos, but it was motivated by other things. There was work by Mandelbrot. We're still in the 70s, by the way. So Mandelbrot looked at this idea of fractals. So a fractal is something that, it's a structure that as you zoom in, you see the same structure, but on a smaller scale. And you zoom in further, you see the same structure. So one of the more famous structures is, there it is. It's this kind of trippy looking. This is the Mandelbrot set. And it comes from looking at an iterated map, not over a real variable, but over a complex variable. And like if we were to zoom in on any of those spiral thingies, we'd see more spiral things. It would look the same. It'd be hard to know, what scale are we looking at? And it was Mandelbrot showed that this isn't just something that happens in dynamics. Lots of things in nature are described by fractals. Like if you look at the coastline of any country, let's say Britain, depending on the size of the ruler you use, you're going to measure a different length to the coastline. So even though the area of Britain is finite, the perimeter is essentially infinite. And so this sort of black region here, it's a finite area, right? But it has an infinite perimeter because as you zoom in, you would just see that it gets more and more intricate. The simplest fractal that I know of is something called the Koch snowflake. You basically start with a triangle, and on each edge of the triangle, so what do you do for the next step? You, for each edge of the triangle, you add another triangle. And you keep repeating this. So for each edge, you add another triangle, and okay, I can't even do it. But hopefully you get the idea. After a while, you'll have something that looks pretty freaky. And it's definitely a finite area, but infinite perimeter. Because at each step, we're multiplying the area, the perimeter by a factor of 4. So 4/3 raised to the nth power is infinity. But we'll stay within a certain box. So fractals, there's a connection between fractals and chaos, and we'll say something about that later. In the 1980s to, I guess, today, let's say, just, widespread interest in chaos, enough that something like this class is happening. So it makes it into the popular culture even. So if you've seen, well, that's cool to see that under a black light. If you've seen Jurassic Park, then you know who this guy is. This is Ian Malcolm, chaotician. You're kind of edgy, wears a leather jacket. There aren't any chaoticians, but I don't know. Right, he gets brought in. It's not really clear why he's brought in, but he's like, hold on, you're going to release dinosaurs in a new environment. You know, things could go in a different direction than you expect very quickly. And so, okay, people appreciate chaos and think that dinosaurs are going to take over or something. It's much more than that, but I think you get it. Right? Once you've made it to the big screen, then you've arrived. So chaos and nonlinear dynamics as a subject matter, as embodied in Jeff Goldblum. There's other things I want to show. Ooh, what's this going to show me? Okay, good. Yeah. There's this is just sort of a selection of applications, kind of more modern and experimental. There's this idea of hysteresis, that depending on how you change a parameter, in this case, this thing called total P, I don't know, I think it's phosphorus in a lake. You can get the lake being clear or dominated by algae. And so that's called turbidity. Like a turbid lake's kind of a nasty looking lake. Related to population dynamics, there was this event in the early 90s, I guess even before then, the cod population in the North Atlantic. So some communities that live in the coast of the North Atlantic depend on cod for their livelihood. So this shows the population of cod. And then it has this huge spike. And so people are probably thinking, yeah, there's going to be plenty of cod forever. And then right after the huge spike, it dips a lot. And then the population almost crashes to zero. So this is something that would be expected under the logistic map as some parameter changes. The zero population becomes a stable equilibrium point, and you don't want that. And so some people are interested in using methods to detect if you're sort of near a bifurcation where population zero is a stable point, because we don't want that. That would be very bad. Here is this thing called something sediment on the y-axis. This is sort of a measure of how, if it's higher on this chart, that means the desert or a region is more lush. And if it's lower, then it's more like a desert. And so this shows that as you go back several thousand years looking at the Sahara, it looks like there was a period of time where it went from, there were lakes and it was green, and then pretty suddenly over geologic time, like maybe over a couple centuries, it becomes a desert. And so that's pretty, like, what happened? There's probably some kind of dynamics thing going on where lush greenery was the stable state, and then all of a sudden desert's the stable state. And dynamics want to go to their stable state. Here's the Earth climate system. So the entire, if you look at temperature, kind of the average Earth temperature going back in time. So this is going back to like almost 20,000 years before the present. There are times, climate is known to be a big deal. And what are the look at nonlinear dynamics tell us about it? We know that there are times when greenhouse gases were higher than today. We know there are times when the temperature was higher. We don't know what all of the main things are, because it's a very complicated system described by ocean dynamics and atmospheric dynamics and the coupling of the two and life, and very, very, very complicated. Navier-Stokes and turbulence is complicated enough. This is more complicated. Financial markets. This is showing financial markets crashing. I guess there was inbred. That's what led to the Great Depression. Is the stock market fell some huge percentage over a few weeks. That was in 1929. Then we had something pretty bad in 1987, and then not so bad in 1997. Could you predict? It may appear unpredictable, but are there kind of universal traits to these things? This is, neural dynamics, migraine attacks, societies collapsing. This is just trying to set the big picture, but that kind of brings us up to today, and then we can talk about some math.